Hi. So my name's Anush. I've been working in the neurotechnology space for over 3 years now. Started in my freshman year. Now I'm in junior year. And most of my time has actually been spent working with consumer hardware. So specifically electroencephalography, which records electrical activities non-invasively from the scalp. So I kind of started off initially inspired by the works of Elon Musk and Neuralink. Decided to get my hands on the Muse 2 EG headset. Muse is a company based out of Toronto making these headsets for meditation. But kind of being this like innate hacker, I was like building these cool little projects. For example, like one of my first projects was using the artifacts that can be extracted from EG, like eye blinks, to control my browser. Another one was like, how do we extract points of interest in content that we consume and create highlights, for example, from a podcast based on when you're interested. And those are just like kind of the start. And then later on, I was able to intern at a company based out of Toronto that's actually using these consumer EEGs for the purpose of clinical biomarkers and essentially fixing the psychiatry pipeline from the ground up using biology. So that was a really fun experience. It kind of opened my eyes to the real impact of neurotechnology. From there, I decided to kind of take it back to the ground roots or grassroots of like where I got the initial inspiration, like companies like Neuralink, Paradromics, Synchron, working on these invasive hardware. Decided to like kind of break down patents from a few different companies. I looked at Neuralink's patent. I looked at Synchron's patent. And that taught me a lot about like the architectures that are used for these custom ASICs and how they're developed, what's the design processes, etc. And then from there, that's kind of what led me to where I am right now. Kind of being frustrated with the go on to the next slide. Yeah, so I was kind of frustrated with one of like the flagship applications of brain computer interfaces, which is motor imagery, right? The task of restoring mobility to physically disabled patients by using their brainwaves. So in this case, if we look at the existing solutions, most of the research grade solutions, in fact, are done using these deep brain implants that are completely wired. So patients that do end up receiving these treatments are trading one disability for another, right? Because they're now restrained to their location. They require these wires, right, to use their implant. Another issue, obviously, there are, for example, deep brain stimulation or deep brain electrodes that are wireless, but these need to be replaced every 3 to 5 years, and that requires surgery again, which is obviously a tedious process for patients. So I kind of thought to myself, what would be the best way, and what's an upcoming technology that could solve the problem in terms of creating truly wireless implants that never need to be replaced. And that's where I started working on Enerspike. And kind of like the key line here is enabling wireless brain computer interfaces using energy efficient neuromorphic computing. Obviously, I don't really need to go super in depth on the background here because you guys at your lab are working with neuromorphics and membristors, etc. But the idea is we could design digital analogs of the biological neuron, which processes spikes, and this is a much more efficient way of processing information and running artificial neural networks for inference, etc. And that's kind of key in the context of neural implants because you are doing a ton of on-chip processing, right? So in terms of what my project entailed, I was looking at a specific data set for two-class motor imagery. So think patients were, I took a data set of 105 patients that were thinking about either moving their hands or feet. Um, Originally I was thinking about acquiring actual invasive data from like electrocardiography or deep brain implants, but obviously that's much more difficult hardware, much more difficult data to acquire. So I ended up using EEG as the best analog for motor imagery. So 105 subjects, 5-second windows, 160 hertz sampling rates. So I had 4,500 samples of people thinking about moving some body part, right? From here, EG is inherently a very noisy signal, super stochastic, random, and filled with a ton of noise. So how do we extract information that's valuable from the signal? That's where spatial and temporal filtering comes into play. Firstly, I knew based on previous research in the space of motor imagery that sensory motor rhythms occur between 8 to 30 hertz. So I applied a bandpass filter within that range to attenuate the frequencies outside of the range of interest. So then I would only get the original EEG signal filtered within 8 to 30 hertz. From there, I applied spatial filtering. The idea is, since we have two classes of data, we could essentially do like classified PCA, where you do like the eigen decomposition, but on two separate classes of covariance matrices. So essentially, the to get a little bit technical here, the principal components that are extracted from common spatial filtering, the ones with the highest eigenvalues, maximize variance for one class of data and minimize variance for the other, and the principal components with the lowest eigenvalues maximize and minimize for the opposite class, so vice versa essentially, and you get principal components that uh, maximize variance and minimize variance in orthogonal vector spaces essentially, right? And what that allows you to do is then train predictive models that do a better job of like creating bounding boxes or creating separations between classes essentially. So if I were to use an SVM, common spatial patterns would definitely help because it's essentially like a kernel, right? Um, in terms of moving on from that time series data, right? After spatial temporal filtering, you're still working in the time domain, but in terms of EEG data, it's traditional to work with frequency components. So I wanted to extract spectrograms where you could see the frequency varying in time from this EEG signal, and traditionally this part of the pipeline is achieved using von Neumann architecture computers running on CPUs, non-spiking, right? But you could actually compute the Fourier transform using time encodings and achieve spiking Fourier transforms on neuromorphic hardware. How do we do that? Well, if we take our original EEG signal, we can encode the amplitude of the EEG signal and have the binary spikes that are outputted in the spike train be proportional, like the time at which binary spike occurs is proportional to the original amplitude of the EEG signal. So parts are like the sampled points at which the signal is higher is binary spikes that occur closer to the starting point or the 0 second point. And you can essentially encode information in these like binary spikes varying in time. And then you can achieve, at the end of the day, like discrete Fourier transform is just a matrix multiplication, right? You could achieve that matrix multiplication using a spiking neural network, and then you basically get the same output, except you're gonna have certain proportionality constants in play, and it's a little bit more complicated than that. And I could explain the full process if anyone's interested at the end of the presentation. But the general idea is you take that spike train, accumulate the voltages of the spike train using the silent stage that you see on the left hand side of the bottom graph. So the silent stage is where you're doing this like dot product essentially, right? And then in the spiking stage, you drive the voltage of that spiking neuron based on some constant current, and then the time it takes for that spiking neuron to cross the voltage threshold at which point it spikes is that latency is actually proportional to the real Fourier transform output, or like the kth element of the Fourier transform. So yeah, I could go deeper into that if anyone's has any questions. But moving on, you'd also want to use some type of predictive model to go from that frequency component to that binary class prediction, right? Either people thinking about moving their hands or feet. In this case, we're dealing with temporal data, obviously frequency components that are varying in time, so time series data. Usually you'd use a recurrent neural network. In the case of spiking hardware, you want to implement or translate non-spiking neural networks into spiking neural networks in ways where you're avoiding as much nonlinearity as possible, because non-linearities like the sigmoid operation and just activation functions in general are more tedious to implement and have more overhead, right? So the idea is the LSTM, which is the state-of-the-art recurrent neural network, has 4 gates, and each gate has nonlinearity, and that obviously adds a ton of overhead to compute memory. At the end of the day, all of these gates are used to produce a memory vector, which is like a representation of the original signal, n time steps before or whatever, right? So what a professor, Chris Elliott Smith specifically, at the University of Waterloo, what he did was he tried to break down, based on first principles, how to implement memory in neural networks using dynamical systems, because we know that we can implement dynamical systems. For example, underneath that first LMU architecture diagram, you'll see that, the equation m sub t equals the A transition matrix times m sub t minus 1, so the memory at the previous time step, plus the input matrix times u sub t, which is like a input signal essentially. That is like a state space representation of a dynamical system. Those type of equations can easily be represented on neuromorphic hardware, and that's also been proven by Chris Smith at the University of Waterloo. So the LMU architecture is perfect to be implemented on neuromorphic hardware. So I decided to use that, and you both test like a non-spiking version of the LMU as well as a spiking version of the LMU. And it's important to note that not only is the LMU more spiking robust, because you're eliminating all these gates in the traditional LSTM, you're going to also save a ton of parameters. And what they found is actually you're going to achieve the same performance. So I'm going to show, even in my results, I was able to find that I'm achieving same performance while considerably decreasing the number of parameters and weights. So in this case, first, comparing the output of the spiking Fourier transform to the Fourier transform that you traditionally compute in NumPy, I found that the root mean square error was 0.0098, so super small, basically indistinguishable outputs between using the spiking approximation versus the normal like CPU version. Now, moving on to like the real results here. If you look at the far right graph, all three models that I tested, the LSTM, LMU, and the spiking LMU, they achieved pretty much the same accuracy. There's a 3% drop off from the LMU to the spiking LMU, because at the end of the day, spiking neural networks are approximations of true like rate coded neural networks, I believe. So what happens is we essentially trade off that 2% accuracy drop off for 2.5 orders of magnitude of energy consumption efficiency. So here in that middle graph, you'll see that energy per inference is on log scale. We're achieving a 240x reduction compared to the LSTM in power consumption, while reducing power consumption from the non-spiking version of the LMU by 2 orders of magnitude, or 70x. And in general, if we use either the LMU or the spiking LMU, we're achieving a 4x reduction in parameter count while maintaining accuracy, essentially, right? So these are crazy results because this has widespread implication both in the space of neurotechnology as well as just biomedical implants in general. So I'm going to speak a little bit about that as well. So in summary, compared to the LMU, that's a 2 orders of magnitude reduction in power consumption and 2.5 orders of magnitude compared to the LSTM. And why is it so power efficient, right? Firstly, spiking neural networks use binary spike trains, like I talked about before. And when you're using binary spike trains, you essentially never have to do any multiplications because dot products just become like reductive sums, right? And then also, the LMU is inherently smaller, right? It's a 4x reduction in parameters. And that just means that you're doing less computations per forward pass, and you're just reducing the amount of power required in general to compute an inference, right? And now what this means is that traditionally neural implants, for example, the Medtronic deep brain implant needs to be replaced every 3 to 5 years. So the projected lifespan is increased by 70x, which far exceeds anyone's human life expectancy. So you eliminate the need for replacement surgeries, and this could potentially extend the use of motor prosthetics to all 100 million people that actually need motor prosthetics, because right now it's only 40 people that are relying on deep brain implants for motor prosthetics. So using neuromorphic methods for doing motor imagery reduces friction, because now these patients don't need to go into a clinic every couple of years to get their hardware replaced. And then obviously beyond neurotechnology, this can be applied to a wide array of biomedical implants that are also have like a fixed lifespan based on their batteries. So in terms of limitations and next steps, this ties into like why I was so excited to find the work that you guys are doing at your lab. First of all, spiking Fourier transform does not outperform equivalent non-spiking hardware accelerators. So there are already on the market Fourier transform accelerators, and these actually use several orders of magnitude less power than spiking Fourier transform. And this was illustrated in other research that I used to base off the pipeline that I developed in my own research. And in terms of latency, doing the inference and computing the spiking Fourier transform is takes a very long time, and it's not within 100 milliseconds, which is the biologically reasonable latency for motor imagery applications. So, trying to cut off on that inference time and simulation time would be the big next step. Also, common spatial patterns that was implemented on CPU in non-spiking manner, or in a non-spiking manner. So the next step would also be to do spatial filtering using the matrix multiplication method used for the Fourier transform, and also expanding the range of recognizable gestures in the motor BCI. And yeah, that's pretty much it.